Yay, I'm live. Sweet. Cool. All right. Testing. Okay. Hopefully that works. Like I said, we're going to be using the information from the textbook today. For those of you in the chat, I've had everybody open up their Chromebooks to access the online textbook. So if you're watching right now, you can do the same thing as well. You can access that online textbook. I'm going to be working out of problems from chapter 5, more specifically, that starts at page 127. That starts at page 127. So you don't have to start like keep clicking. If you type in 127 into the online textbook, it'll take you to page 127, and we'll get there. In regards to the first marking period, I already said that before. I'll say it again. I will have everything in by tomorrow. Grades are due tomorrow. I'm hoping to be clicking submit before I leave the building today, and that'll be fun. Furthermore, today is the first afternoon of these Google Meet sessions. Oh, happy day. Are you so excited for 10 minutes of chaos in every single class? Yay. Again, the Google Meet for this afternoon that is set specifically for all my classes, they're office hours. And it's mainly like if you have questions, pop in. If you need clarification on something, pop in. But honestly, if you don't need anything, then you don't really have to pop in. It's just going to be chaos when your teacher is like 2 minutes late, and then you're in the middle of answering a question, and then they have to pop into another Google Meet. It's gonna be chaos. I don't know. I'm not going to sugarcoat it. It's just going to be chaos. Someone yelled good morning at me. So apparently some students still have manners. No, there were several of you that said good morning, and I scowled at you. So anyway, I'm so out of it right now. You want to see a picture of my daughter? Nobody responds. Hold on. I'll show you a picture of her, just because it's the greatest picture that was ever taken. This is by far the greatest picture that has ever been taken of my daughter. Oh, someone get that. Look at her. Look at her in all of her glory. Look at that. I'm just saying. Look at her dress. Now look at her dress real quick, right? My son looked at that dress. Wait, my screen froze. Hold on. My son looked at that dress, and you know what he called it? Her Wawa dress. Called it her Wawa dress. Thought it was great. Anyway, that's neither here nor there. But that's my daughter. She's cute. Cuter than everyone. Anyway, so here's what I would like to do. In your online textbook, if I can actually get the page right here. What in the heck? Hold on, I got to zoom back out now. Display settings, zoom back out. Oh, I hate this thing so much. What in the world? Why is it off to the side? Okay, let's go to page 128 then. Good. Then we go back to 127. Good. See, this is why I wanted you to have your online textbook open so that you could see it better than I could. Excellent. Let's start very simply. Let's start with a problem like number 9. Let's go down to number 9. I'm on page 127. And I'm looking down at number 9. And this is perfect, especially for those in the chat, because obviously if you can't see the page because of the glare, you at least have your online textbook open at home. But I'm looking at something like number 9. Now, here's the other thing that I'm going to ask for. Yes, you have the online textbook open. But I am also going to ask for those notebooks to be out and open. Because any problem that we go over, I would like you to have that information written down in a concrete place so that we can move forward with it. This information on the normal distribution is going to play a role moving forward in a lot of future chapters. We'll talk about that when the time comes. So hold on. Come on, microphone. There we go. So I'm looking at number 9. Number 9 says the mean score on the stats exam was 75 points. With a standard deviation of 5 points, and Gregor's Z-score was -2. How many points did he score? So hold on, let me write down some of this information. Just in terms of a title, because I'm going to give you a title in a moment. Let's just call this normal distribution practice. And today is the 17th. Today is the 17th, right? Yeah, it is. Excellent. And I'm looking at a problem like number 9. The mean score on the stats exam was 75 points. That won't be the last time that happens to somebody. I promise. The mean score was 75 points with a standard deviation of 5. And Gregor's z-score was a -2. We'll flip that back, zoom back out. Here's what we got with number 9. Now, there's a lot of things that you can tell based on Gregor's z-score. Because Gregor's z-score is negative average, scored below average. He scored a -2 in terms of his z-score. Now, I gave you a definition that basically stated that if you are more than 2 standard deviations away from the mean, then you are considered an unusual data point. You are considered unusual if you are more than 2 standard deviations away from the mean. Now, he's borderline -2, so he's just like right at the cusp of like, kind of unusual, but like not, I don't know, right on the cusp. Poor Gregor. But the question is, what did he score? What did he score? Let me see here. Did they give us any other information? No, just 75, 5 points, and -2. What you need is this. You need to know that a z-score is calculated with x minus the mean divided by the standard deviation. And from here, it's just like an algebra problem. The algebra problem in this case would be, well, -2 equals x minus 75 over 5. And that's what we have to solve. You have to make sure that you're putting the right numbers into the right location. And of course, using those algebra skills. Now, being that you are an AP Stat, I can assume that you have all been through at least Algebra 2, correct? Yeah, good for you. I'm going to multiply by 5. I'm going to add 75 to both sides. Oh, poor Gregor. Scored a 65. But that's what it comes down to. That's the information that they're giving us for this problem, and that's what he scored. Oh, well. Now, there comes a point, and I want you to think about this realistically. There comes a cap in terms of how many standard deviations you can score, let's say, better than the mean. Assuming that it's a 0 to 100 scale, in this particular instance, there actually is a maximum value that you can get. So I believe it's like, what, 5? Yeah, it's like 5 as a z-score. Now, you get 5 as a z-score. That is extraordinary, amazing, good for you, fantastic. But you can't score higher than a z-score of 5 for this particular problem. Unless the teacher gives extra credit. In that case, well, they're weak. Don't give extra credit. All right. Let's jump down to a problem like number 12. Let's jump down to number 12. Placement exams. Now I'm going to attempt to zoom in a little bit. Come on, you. It won't let me like move over with this. What in the world? I hate the internet and everything that it stands for. Fine, I'm not going to zoom in. I'm not going to bother with that. But I do hate the internet. Anyway, number 12, an incoming freshman took her college's placement exams in French and mathematics. In French, now hold on, let me write down some of this information for myself. In French, she scored an 82. And in math, an 86. So hold on. French scored an 82. Math scored an 86. Just writing down the important information. The overall results on the French exam had a mean of 72 and a standard deviation of 8, while the mean math score was 68 with a standard deviation of 12. Okay. On which exam did she do better compared with the other freshmen? Okay, so I'll just double check all my information. 82 on French, 86 in math, 72 mean, 8 standard deviation, 68 mean, 12 standard deviation. Good. Boom. Zooming in, zooming in, zooming in. The question becomes, on which one did she do better compared with the other freshmen? Now, clearly, she scored raw score better on the math exam. And you could say, well, yeah, better on the math exam. Well, that doesn't prove anything. With the way that the question is worded, with the information that they're giving you with mean and standard deviation. And let me go back to the wording of the question real quick. The question says, on which exam did she do better compared with the other freshmen? Now you're doing a comparison, but you're comparing a French exam to a math exam. That's comparing apples and oranges. The best way to do a comparison is to look at your z-scores. You got to look at z-scores in order to do the proper comparison. Because, I don't know, math is the pinnacle of all human existence, and French is just French. I'm just saying. French is dumb. Fight me. Anyway, so back to this. Please, somebody tell Madam Morse. Let's see. 82 minus 72 divided by 8. 86 minus 68 over 12. I'm going to calculate their z-scores using that proper formula. So let's see what happens here. 10 divided by 8, I'm just going to get the decimal. That's a 1.25. Again, clearly better than average. Better than average. Let's see what the math z-score was. 86 minus 68. Clearly a much higher deviation. Divided by 12. Aha! 1.5. The question then is, again, I go back to the question. On which exam did she do better compared with the other freshmen? Well, compared with the other freshmen, she did better on the math exam. Because, and again, when it comes to a statistical conclusion, you can't just give a number. Sometimes you do have to give a proper interpretation. You would say she did better on the math exam because when the scores were converted to z-scores, the math z-score was higher. Z-scores are the standardized ruler. Now, this obviously you wouldn't write the rest of this stuff, but z-scores are the standardized ruler by which you can compare two different things, like long jumpers and shot putters and apples and oranges. Just saying. Let's see here. Actually, I probably should have the chat open on my phone just in case. I should have the chat open just in case, because I'm sitting over here and I don't want to keep having to peek over at the computer. Come on. There we go. Getting that YouTube open. Excellent. Good. Okay. Let's see. I'm going to jump to the next page. I'm going to jump to page 128. So you can all click over there. And, oh, there we go. Let's look at number 18. We're going to look at number 18. Now, fun fact about these problems. I purposefully did not look up the answers to any of these questions. I purposefully did not look up the answers to any of these questions because I wanted you to see how you could properly think and dissect these problems. Number 18. John Beale of Stanford, California, recorded the speeds of cars driving past his house, where the speed limit was 20 miles an hour. The mean of 100 readings was 23.84 miles per hour with a standard deviation of 3.56. He actually recorded every car for a 2-month period. That's funny. There are 100 representative readings. Okay, whatever. How many standard deviations from the mean would a car going under the speed limit be? Okay, hold on. Let's talk about this. First, let me write down some information for myself, and then I'll go to part B. First of all, the speed limit was 20 miles an hour. He took a mean of 100 readings. I'm writing an extra little piece of information there. And I'll explain what this is in a moment. Standard deviation of 3.56. Okay? And the question is, how many standard deviations would a car going under the speed limit be? Okay. So here's what I've wrote down so far. Now, even though this at the moment is not going to affect the problem that I asked about standard deviations to be under the speed limit. But I wrote down n equals 100 because there were 100 trials. There were 100 trials dealing with that stuff. Okay. The mean is 2384. The standard deviation is 3.56. If you notice for a moment, notice the type of notation that I've been using all morning. I've been using X bar and S. X bar and S are dealing with sample statistics. So just for the sake of argument, I considered the first problem we did? Gregor's Z-score on everybody in the class taking that test. I consider that a sample. Because if you wanted a population, you'd have to take like everybody who's ever taken the test in the history of this teacher. I don't know. Same thing with the French and the math exam. You're comparing the other students to that one sample of students taking the test. One could argue that, well, since you're sampling every student, couldn't it be a population? Yes, you could argue that. I don't know. But anyway, back to this. X minus 23.84 divided by 3.56 less than 20. And I set up a little inequality here. Let me go back to the problem. Number 18, A, how many standard deviations from the mean would a car going under the speed limit be? Under the speed limit, I have, what did I put 20 there? I apologize. What did I put 20 there? That's just ridiculous. I don't know why I put 20 there. I should erase that. Again, what does this actually calculate for me? Z-score. This calculates the Z-score. I had a little like one of those brain malfunctions. Like, what are you talking about? Z-score less than 20 miles an hour? That makes no sense. Erase that from my memory. This would calculate the Z-score with whatever number I put in. The Z-score of the sample that he was doing. Now, if you had somebody who was driving under the speed limit, just for the sake of argument, I am going to put a 20 into that spot for X. Now, yes, this would calculate the Z-score for someone who was driving exactly 20 miles an hour. Now, that doesn't exactly answer the question, but let's just see what happens with this problem. Let's just see what happens when I do this calculation. Boom. I type that in. I get approximately negative 1.08 is what it rounds to. Negative 1.08 is what it rounds to. Now, this does make sense in the idea that, yes, well, somebody's driving under his average. That means they have a negative Z-score. 20 miles an hour is the speed limit, so they would be within the legal requirement. But again, that's not what the question is asking. They're asking specifically about the number of standard deviations. Number 18, how many standard deviations from the mean would a car going under the speed limit be? Well, basically, anybody more than 1.08 standard deviations below the mean would be going under the speed limit. That's the proper interpretation. A Z-score is the number of standard deviations you are away from the mean. A Z-score is the number of standard deviations you are away from the mean. So somebody going exactly 20 miles an hour, there's their z-score. They're approximately 1.08 standard deviations under the mean. Anybody less than that, anybody more than 1.08 standard deviations under the mean would be going under the speed limit. That's a weird problem. I keep getting hung up on the wording. I hate the way they word these problems. Which would be more unusual? Which would be more unusual? Part B. Same problem. Part B. I already talked about this definition. A car traveling 34 miles an hour or one going 10 miles an hour? What's the speed limit? 20? Isn't it 25 in most residential areas? If you see someone going like 10 miles an hour past your house, don't you automatically think creeper? Okay, yeah, several people nodding yes. All right. So 34, 23.84. Oh, goodness. Divided by 3.56. I'm going to do two calculations. I'm just writing it down, and then I'll switch the camera over. 10 minus 23.84 divided by 3.56. This marker's dying on me. Move that up here. Let's pretend I made it in. Nothing? All right, whatever. Let's do the calculation. Now, again, I talked about this last time. I'm going to zoom in again just to show you, just to make sure we're all on the same page with this. But when you do this calculation, it's best to use parentheses. It's best to use parentheses around the top of the fraction. And just please get in that habit. Let me do this calculation as well. Parentheses 10 minus 23.84 divided by 3.56. Oh, interesting. They are both unusual. They are both unusual in terms of their z-score. 34 miles an hour got you a z-score of approximately 2.85. And 10 miles an hour got you a z-score of negative 3.89. They're both unusual. But you got to look back at what the question is asking. The question is not asking, are these miles per hour, are these speeds unusual? Part B, which would be more unusual? A car traveling 34 or one traveling 10 miles an hour? Clearly, it's the one traveling 10 miles an hour. Clearly. I don't know. I'll tell you a story. One time, it was like Christmas time in my parents' house. My parents still live there in Settlers. You all know where Mizzen is? Cool. My parents still live on Mizzen. And my sister had this like big SUV truck parked in front of the house. And it was like Christmas time, snow's coming down, it's dark, we're all inside the house, kind of like, settling in after dinner. And there was this like screeching noise and all of a sudden this loud bang. And then we walk out onto the lawn, and this guy apparently at the beginning of Mizzen had begun like going left, right, hitting a bunch of cars, left, right, scraping by them, and then slammed underneath my sister's SUV. There's no point to that story. I just thought I'd say that. Anyway, I don't know, driving in a residential area. Okay, speaking of cars, let's jump to number 25. Let's jump to number 25 because this is going to really deep dive this kind of thing. Number 25. Environmental Protection Agency fuel economy estimates for automobile, models tested recently predicted a mean. Hold on, let me write some of the stuff down. As I'm reading it, it's always a good idea to write some of the stuff down. They recently predicted a mean of 24.8 and a standard deviation of 6.2 for highway driving. Now, I want you to notice something here. They estimate for car models tested recently predicted a mean of 24.8 and a standard deviation of 6.2. It could be acceptable because these are the numbers being reported by the EPA from testing. It is reasonable to use population parameter notation. You could use mu and sigma if you wanted to. You could argue for X bar and S. You could argue for that based on the fact that this is like testing and all that fun stuff. And most likely it was a sample of cars that they did this from. I just want you to know what your options are. Just for funsies, I'm going to use mu and sigma. but that's just for funsies. 24.8, and sigma is 6.2. Okay. Assume that a normal model can be applied. I want to be very clear about something. I want to be very, very clear about something. They're telling you to assume a normal model can be applied. This is very important right here. In the future, you may come across a problem where it doesn't tell you that, and you have to go about the process to show that the data that they give you is normally distributed. You can't assume that the data is normally distributed unless they tell you the data is normally distributed. It's one of those weird catch-22 things. If they don't tell you the data is normally distributed, then there's going to be something else in the problem that implies or gives you enough information to show that it's normally distributed. Typically, they would give you like a bunch of data points and then be like, okay, let me look at the histogram, type it all into the calculator, look at the histogram, it looks nearly normal. Okay, I can proceed. But when they tell you, assume a normal model, that's Christmas come early. And I say this for a lot of future chapters that we're going to be covering. If they tell you to assume a normal model, then that just saved you a ton of work. Just saying. So let me assume a normal model. You know what happens when you assume, right? Do you? It makes a bad word out of you. And you. Nobody gets me. Anyway, part A. Draw the model for auto fuel economy. Clearly label it, showing the 68, 95, 99.7 rule predicts. Or showing it what the rule predicts. What's the other name for that rule, by the way? The 68, 95, 99.7 rule? It's the empirical rule. Good. Now, again, I want you to be aware. They may use one or the other. You may come across free response questions that use the phrasing empirical rule, and I just want you to be aware of that. So we have to create a normal model using that rule. So this is what you're going to do. You're going to draw a normal curve. You got to get used to drawing these normal curves. Do them in the best that you can. That one was actually pretty good for me. I mean, it's a little off to the right, but whatever. I don't care. Pull dotted line straight up and down. I'm going to put 24.8 right in the middle. 24.8 is the mean. That is what we're dealing with. And then I got to start doing these little thingies. These three are +1, +2, and +3 standard deviations. So I'm literally going to go to the calculator. 24.8 plus 6.2. I got 31. Plus 6.2. 37.2. Plus 6.2. 43.4. Cool. Zoom in a little. But then I got to do the same thing on the other side. Again, I don't even know what all the rest of the questions are asking. I'm just kind of dealing with this as we're kind of going along. There's one over there. There's one right there. And there's one right there. It doesn't have to be perfect. It doesn't have to be absolutely perfect, but it has to be pretty close when you draw these things out. And be careful when you draw these things out. Don't just do them willy-nilly. You got to make sure that you're taking care of them. 18.6, 12.4, 6.2. I'm not done yet with this part. I still have to label some stuff. Do you guys remember, what do these numbers represent again? I'm sorry, let me rephrase. What do these numbers represent in the context of the problem? Miles per gallon. Yeah, no, you're correct in the standard deviation statement, but I forgot to say context of the problem. These are miles per gallon. Miles per gallon. It's a French word. Ugh. Anyway, now the interesting thing is, in terms of miles per gallon, clearly, what's going to happen if I move over one more standard deviation to the left? Yeah, like, okay. 0 miles to the gallon? There's nothing beyond that. You can't go negative miles per gallon. That'd be weird. Velocity versus speed, huh? You guys know the deal? Velocity versus speed? Okay. Okay. Just saying. I don't know. But anyway, let me go back to the question. The question said, draw the model, clearly label it. Okay. Miles per gallon. Okay. I'm going to give it one more thing. EPA estimates. That's my title. EPA estimates. Maybe I'll put miles per gallon right there. I don't know. I really don't have to give it much more. I just kind of felt like giving it a title because whenever I draw something like this, I want to give it a title. I forgot one more thing. There's one more thing we forgot to clearly label it with. Do you know what it is? Do you know? It's the percentages. You got to label it with the percentages. 68% for -1 to +1 standard deviation. 95% for -2 to +2 standard deviation. And 99.7% for -3 to +3 standard deviations. Excellent. This is a complete first problem here. Excellent. Or part A, I should say. Nice. And we're going to use this. We're going to use this for what the next few problems are going to say. Let's see. Part B. In what interval? Oh, we already know this answer. Part B. In what interval would you expect the central 68% of autos to be found? Because of the picture that we drew, we already know that answer. Let me bring up my next page. Part B. The central 68% of cars, I can spell cars today, are between 18.6 and 31 miles per gallon. Done. We already did the legwork for that. Now, again, that's according to the empirical rule. Then it says about what percent, this is part C, about what percent of autos should get more than 31 miles per gallon? Well, 31 miles per gallon. Let me go up to the board real quick. I got an orange marker here. More than 31 miles per gallon is more than just this wedge. More than 31 miles per gallon would take you all the way out over there. Question. First, what's 100% minus 68%? 32%. 32% are outside of that middle range. 32% is outside of that middle range of 68%. But of course, they're only asking for one side. These things are symmetric. So what's my answer? Second? 16. It's 16. Yeah, 16%. That's it. That's all you got to do. Done. We already created this picture. This picture was the end-all, be-all of this whole thing. This picture basically got the thing done for us. Yay! It's great. I love it so much. Oh, I'll get rid of that. There we go. Good. Good. Yeah. Goodness gracious. Here, give me 1 second. I gotta type one thing on the computer. Click. I gotta type one thing on the computer. Jump to the next part, by the way. The part to D on there. I gotta do one thing here real quick. Come on, you. I can actually do this correctly. Excellent. Cool. Unfreeze. There we go. What's part D saying? Describe the gas mileage of the worst 2.5% of all cars. Oh, wait, no, I already skipped that. That was part E, right? Whatever. I'm going to put 16% here. What's part D? Part D, about what percent would you get between 31 and 37.2? Come on, you. 31 and 37.2. Hey, we did something like this last class, didn't we? This one right here. Do you guys remember what we got last class? Yeah? 13.5, approximately. Absolutely. 13.5. Get my orange marker here. Just kind of throw this in here. Now, first of all, we know that everything going this way is 16%. We did the same thing for right here. Going that way, if you did it with the 95%, it'd be like, okay, 95% in the middle, 5% outers, 2.5, 2.5. This should be 2.5% going that way. So then if you just subtract that off, yeah, you get 13.5% approximately. Now, I'm going to do something in the calculator in a few minutes that is going to get the exact values for some of these problems. But we'll talk about that in a few moments. But yeah, using the empirical rule, using this chart, you can absolutely figure out what is supposed to be in each section. So what did we say? 13.5%. I'm just writing my answers down at the bottom while keeping this chart up. Part D, I keep reading letters wrong. E, describe the gas mileage of the worst 2.5% of all cars. The worst 2.5% of all cars. Now, 2.5%, as we've talked about, here's the middle 95, meaning 5% is split between the left and the right, meaning this is the worst 2.5%. And if that is the worst 2.5%, then you could say, well, if I have to describe it, the worst 2.5% of gas mileage would be 12.4 miles per gallon or less. That's how you would write that out. Okay, the worst 2.5% of all gas mileage is about 12.4 miles per gallon or less. That's what that thing would do. Oh, it's so weird. I love it. There we go. Let me go to my calculator real quick for some of these problems. And you guys obviously have a graphing calculator set up for you. Check this out. First of all, let's talk about part B real quick. On that problem, part B. Part B asked for the middle 68%. Now, obviously, if you're doing the empirical rule, you got it. There it is. Oh, happy day. But just for the sake of argument, look what I'm typing in here. Now, on your graphing calculator, you don't have this exact same interface. The interface that you have, if you go to second vars and go to normal CDF, which is the second option, the interface that you have says lower, upper, mu, sigma. Well, those four numbers are the four numbers that I just typed in, which would be 18.6, 31, 24.8, 6.2. The mean and the standard deviation always go third and fourth. If you do that, then clearly it's like, oh, well, that's the central 68%. Well, it's technically the middle 68.3%. It's technically the middle 68.3%. But if you're using the empirical rule, it is acceptable. It is perfectly acceptable to have a rounded number like that. Say, oh, 68%. Cool. What about part C? Part C said, okay, what about more than 31? More than 31. Check this out. Oh my gosh. More than 31. I'm going to show you how, or my rationale for writing this out. What's my upper limit? What is my upper limit there? Do y'all see that? What did I type? Like 1 million or some junk like that? Spoiler, it doesn't matter what number you type in. As long as that number is very large. As long as that number is very large, you're fine. As long as that number is very large. There's a couple of different ways to kind of go about this, but as long as that number is very large, you should be fine. Chapow. Yeah. We wrote 16% because of the empirical rule. The exact answer is actually about 15.9%, which is like, you're splitting hairs at that point. You're splitting hairs. But here's the thing. If the problem implies, like this one did, to use the empirical rule, then you are well within your right to use the empirical rule as you see it in front of you right now. In fact, AP graders can't fault you for that. They can't. They can't fault you for that. There will come a time when you can't use the empirical rule. For example, give me a number that's like somewhere in the middle between 12.4 and 18.6. 16. All right, cool. 16 miles per gallon. Check this junk out. Oh my gosh. We're going to do this one together. There's 16 miles per gallon. Check this out. What if I asked you, what percent of cars have a gas mileage less than 16 miles per gallon? Now, somebody might try to do a little, fancy bit of mathematical division, like, okay, I'm going to split this in half, I'm going to split this in half. No, you're not allowed to do that. The normal curve doesn't have a consistent height. And because the normal curve doesn't have a consistent height, you can't just try to do some fancy, I'm going to divide this in half, I'm going to divide that in half. You can't do that. Here's what you would have to do. You would have to use your normal CDF. In fact, let's go there now. I'm going to do normal CDF. Now, yes, your mean and standard deviation are going to remain the same. Your mean is going to be 24.8. Your standard deviation is going to be 6.2. Fantastic. Here's my question. What do I put in for my limits? What do I put in for my lower and upper limit? Ooh. Ouch. Can you tell me either one of them, lower or upper? Yeah. Definitely. Upper would be 16. What's my lower? I want to go a little bit more in depth than that. A negative large number. Some giant negative large number. Doesn't matter what that large number is. Just make sure that it's negative. You could totally do 0, and this is why I brought this up earlier. Technically, you would be allowed to do 0 because 0 is the lowest miles per gallon that you could possibly get. But because of the way that the normal curve works, you would get a slightly different answer if you didn't put in the giant negative number. I would prefer that you put in that giant negative number. I'm going to show you both calculations right now. I'm going to show you both calculations. So I don't know why I put a comma in there. Here's my giant negative number, comma 16, comma 24.8, comma 6.2. Chapow. And I get approximately 7.8%. But if I did that calculation again with 0, I do get the same answer. But if you notice, some of these decimals are off. It's simply because when you get to 0, there's still tiny bits of percentage after the fact that you need to be aware of. Yes, it will not change the answer on like an AP test or some junk like that. I just wanted you to get in that habit. You need to get in the habit that if you're using the normal curve with lower and upper limits, and you're going off the end far to the left or far to the right, you either have to put in a big negative number or a big positive number. Let's look back at part E again. We know what the answer is to part E. We know that the answer to part E is 12.4 miles per gallon or less. Go to your calculators. Go to your calculators. Hit second bars. Go down to inverse norm. Now, I introduced very briefly at the end of class something with inverse norm. On your calculators, it doesn't have the same interface that mine does. In fact, you have 4 options. The first option being area, the second option being mu, and the third option being sigma. Well, you know what mu and sigma are for this problem. And then the fourth option, does it give you an option for left, center, and right? Cool. Leave it on left for now. Leave it on left for now. We're going to talk about what that is in a moment. Mine doesn't have that. That's okay. Since mine doesn't have that, it's automatically set to left, just for the sake of argument. But we need to figure out, okay, where's the worst 2.5%? Where's the worst 2.5% of data points in this problem? I'm going to type in, and this is what you would type in for area. This is what you would type in for area, 0.025, comma. Now, I'm sorry, you wouldn't put the comma in. I would put the comma in. But then after that, 24.8 for my mean, 6.2 for my standard deviation. Keep it on the left. Hit enter, or it doesn't say paste or calculate. Paste. Hit paste and then hit enter again. And you should get the answer that I got. Now again, we already knew this answer. We already knew it was like 12.4 approximately. The exact answer is actually about 12.6, 12.65 or some junk like that. The exact answer is about 12.6. The answer that we wrote down was 12.4. Yes, there's a difference. But the answer that we wrote down was based on the empirical rule, and the answer that the calculator got is more of the exact answer based on some more advanced calculations. An AP grader should be able to accept either one as long as you show them what you did. If you use the empirical rule, then you should have a picture of the normal curve with the 68, 95, 99.7 percentages on there. If you used the calculator to do that, then you would literally write out this calculation. I would literally write it, inverse norm, parentheses, 22, I would write that out and then show the answer. And then give a proper interpretation. The worst 2.5% of gas mileages are about 12.6 miles per gallon or less. That would be appropriate. That would be appropriate. Just for the sake of argument, go back to inverse norm real quick. Go back to inverse norm. Change left to say right. Do all the other numbers, are they still there? Cool. But change left to right. You just got to hit enter on the word right, I think. And then go to like paste and calculate. Do that. Tell me what number you got. 36.95. Check this out. Got it. Look what I just typed in on the screen. You said 36.95? Why is that? Why is that? The question asked for part E for the worst 2.5%, right? My cap. My day is over. Anyway, what I found right here was actually along the lines of the best 2.5%. It's on the other side, like you said, you know. In fact, check this out. This was like 16 point, not 16. I'm going to write it there, 12.6, which is the worst 2.5%. And this would be the best 2.5%. You use the word, you use the percentile. The calculation for 12.6 is what they call the 2.5th percentile. The calculation for what I just did right here is for the 97.5th percentile, is what they call it. Go back to inverse norm, change it to center. Change it to center and hit enter. I want to see what it actually gives you guys on there. Does it give you two numbers? It gives you two numbers because those are quite literally the middle 2.5% of all data points. It's the middle 2.5% of all data points. Go back to inverse norm one more time. Go back to inverse norm one more time. Keep it on center. Keep it on center. But instead of, what do you have typed there? 0.025? Change it to 0.68. Change it to 0.68. You get two numbers again, all right? But what are what's the first number? 18.63. Nice, which we got 18.6 on the empirical rule. What's the top number? Say it one more time. 30.97, which we got 31. The numbers that you just got are the exact middle 68%. And these numbers are just the approximate middle 68%. Here's what I need you to recognize. Normal CDF. Normal CDF, you put in the data points, and what it spits out is the percentage between the two data points. What percentage of the curve are between those two data points? Inverse norm, you put in the percentage, and it spits out the data point at that percentile. Or in the case of the center, which you wouldn't really use that much often. Actually, you guys probably have an advantage over what I do. Because if I had to find like the middle 2.5%, I want you to think about this for a second. If I had to find the middle 2.5%, I would have to do something like this. The middle 2.5%. What percent of the graph am I not including? What's 100 minus 2.5? Divide it by 2. Somebody double check them. Somebody double check them. 48.75. Should beat you to it. 48.75, 48.75. I would have to find the 48.75th percentile, if I can spell that right. And then I would have to find the 51st point, 51.25th percentile. I would have to calculate those separately, whereas you just have something on the calculator that just says center, enter, done. Good for you. Anyway, here's what's going to happen. Here's what's going to happen. Before I leave here today, I am going to pick out a few problems from the textbook that we have not gone over. I was very deliberate on a lot of these problems that we went over. But I want to give you a couple of problems to try, just a few. Not a lot, a few. And I want you to work on them before you come here on Thursday. On Thursday, I would like to take a little bit of time to review said problems before we wrap up this chapter. there will be an assessment that I will talk more about on Thursday. It's not going to be on Thursday. It's not going to be on Thursday. So breathe. But there will be an assessment on Chapter 5 before Thanksgiving break. I'll talk more about that on Thursday. So in the meantime, what you can do, again, I'm going to assign these problems before I leave today. I'm going to put them on Google Classroom. You can read through the chapter. You can try these problems. And then on Thursday, we'll recap everything that we need to know before we knock out whatever assessment is on the way. And then maybe we'll be home for the rest of our lives. I don't know. It's going to be a fun time. Anyway, I'm going to sign off. Bell's going to ring in about 20 seconds. Yeah, we did it.